let's revisit the most important proof, the stability of parameter adaptation algorithms. The key concept that we talked about last time is passivity, characterized by this Popov inequality, where the supply to this system is lower bounded by some negative numbers for any t, and then for any input. Regardless of what kind of input you supply to the system, the product between the input and output will be lower bounded by this value. Let's say intuitively it can be understood from this way. Based on energy conservation for a physical system, energy at a future time, t1, will be less than or equal to, if it's passive, if the system does not generate energy itself, then the future energy will be upper bounded by original energy plus the supplied energy to the system. And then, because energy as a physical quantity is always non-negative, so the boundary condition for this to happen is this one is always going to be larger than or equal to 0. So therefore, this right-hand side is going to be bounded from bottom by 0. So therefore, we have this Popov inequality. And it's a negative sign, right? And because energy is again non-negative, that's why it is a negative gamma square. That's all the back-end stories about this definition over here. And the power of this passive system concept is this will be able to formulate this feedback loop where we said actually our goal is to make the top part to be a linear time invariant system and the bottom part can be nonlinear. And if both of them are passive, then from our example last time, the whole system is going to be passive. And if one of them is strictly passive, then we can have a stronger condition related to stability. So let's state this key concept first and then talk about how to discuss the passivity for the bottom and the top part. The hyperstability theory there are two versions. First is the easier version, the less restrictive version, hyperstability. The feedback block is hyperstable if and only if, IFF, it's if and only if. The nonlinear block satisfies the Popov inequality and the top part, the LTI system, is positive real. PR. This is the user's version to obtain hyperstability. What we talked about here is the concept, the passivity concept. And if you are going to put the concept into practice, then these are the things to check. You're going to check the LTI is positive real. The detailed definition of positive real I will provide in a minute. And then you're going to verify the bottom part, the nonlinear part, is satisfying the Popov inequality. And then asymptotic hyperstability is to add so asymptotic hyperstability, it's going to require the same for the nonlinear block. It's just going to add a few extra conditions for the LTI block. Is strictly positive real. SPR. So that's the full statement for hyperstability and asymptotic hyperstability. The interesting thing here is for asymptotic hyperstability, we're only requiring some more extra from the LTI block and not the nonlinear block. And the reason, if you recall, our focus last time is, our focus is on state X in the LTI block. All right? It's going to turn out, if the LTI block is strictly positive real, then we can induce very nice properties about X without requiring too much on here, too much extra on here. It has to satisfy the Popov inequality. I would like to, my plan is to talk about this version first. I talk about the stronger version first, and then I'm going to talk about the positive real version, the slightly relaxed version of hyperstability. All right? A stronger requirement is easier to discuss than the less restrictive version. So, definition is as follows. For SPR, for continuous time system, we say a transfer function is SPR if it doesn't have any poles, unstable poles, the transfer function shouldn't have unstable poles in the right half plane. So the real part of S being positive is the right half plane. It's actually the closed right half plane. So the transfer function doesn't have any poles in this right half plane, and then it doesn't have any poles on the imaginary axis. So it is strictly stable. And then for any frequency value, if you do the frequency response of the transfer function, you're going to obtain this condition that the real part of the frequency response of this transfer function is always positive. Hence the name, positive, strictly positive real. Okay? These are the most commonly used approach to evaluate SPR functions. This is the continuous time version. For the discrete time version, it's similar. we say a transfer function GZ is SPR if it satisfies two conditions. First of all, GZ doesn't have unstable poles, essentially. So for discrete time systems, unstable poles are outside of the unit circle. So and then this is strictly outside of the unit circle. So should be no poles outside of the unit circle, and then on and on outside of and on the unit circle. So there are no marginary poles on this unit circle. And then same thing, if you take the frequency response, the real part of this frequency response is strictly positive. As a recap, if I have a discrete time transfer function, the way to obtain a frequency response is to replace z by ej omega and evaluate omega along this unit circle. So it's from pi to negative pi. And if you do that, the real part of this complex number should always be positive. That's the definition. Before we discuss about the details, let's take a look at what this means. These are actually strong conditions in a way. First of all, if it's SPR, you already see that it has to be stable, strictly stable. Doesn't have any unstable poles, doesn't have any marginally stable poles. And second, it requires this frequency response to also lie on this right half plane strictly. And that's not necessarily always satisfied. Even if a stable transfer function doesn't always have this property. Right? I will do one example for this case. Same idea here. Let's talk about some examples. If I'm just a constant transfer function, so it's a static gain for the system, then you can see, first of all, let's think about, is this system passive or not? All right? So we already said passivity is closely connected to transfer function for linear time invariant systems related to SPR conditions. If we take a look at this system, if I check for any input V, the output W is going to be C times V, so W transpose V is going to be C V square, right? So and then obviously this is going to be lower bounded by, if I factor out C, this is the integration of a positive number, so this one is always positive, and then this is obviously bounded by C times a positive number. If C is a positive number itself, then this is lower bounded by 0, right? So definitely I can lower bound this number. This system is definitely passive. And more intuitively, obviously, it doesn't generate energy. You are just applying constant gain. No energy is generated. right? But we don't want to always do this, right? Whenever we see a transfer function. This is a more practical way to check. So the way to check is as follows. First of all, GZ indeed no unstable poles. Even marginally unstable poles doesn't exist. And second, the frequency response, that's very easy to evaluate. It's always actually C. And then, therefore, the real part of the frequency response it's C, and it's going to be, therefore, positive. The system is going to be positive real if C is positive. Okay? So that's the evaluation of the criteria here. And if you pay attention to what we discussed here, there was actually a little loophole here. So when I say this can be lower bounded, that is, if C is positive, then it is obviously lower bounded, right? If C is negative, then it's not guaranteed we can lower bound this. Because this integration can be very, very large. As t increases, this is a very large positive number. And if this is negative, we won't be able to lower bound that for sure. Okay? So the C positive is a requirement for this to be SPR. This is obviously too simple. Let's check something that's more practical. Let's check this one, integrator. I'm going to do .5. No. In the general case, actually. So let's check this first order discrete time system. If A is 1, then this is a discrete time similar to the integration process. Let's consider the case A is less than 1, the absolute value. All right, so the pole is Z equal to A. So therefore, this pole is inside the unit circle. It is always stable. Then let's check the frequency response. In practice, you will do MATLAB or Python. But for this first order system, if you check by evaluation, you can see the frequency response will not be guaranteed to be always on the right half plane. So to check, let's add G ej omega with its complex conjugate and obtain just some minor calculations. The denominator and then the numerator is going to be E negative j omega minus A plus E j omega minus A. All right? Let's pick some extreme values, and then we'll be able to see that this is not guaranteed to be positive. Let's pick omega equal to negative pi. we're going to have ej omega becomes, so this is a unit circle. As you evaluate omega from pi to negative pi, ej omega is this complex number that rotates within this unit circle. So ej omega pi, ej omega when omega equals negative pi is going to be negative 1. And e negative j omega is also going to be negative 1. Then this number here is going to become negative 1 minus a square, negative 1 minus a, negative 1 minus a. Then immediately we can see numerator, the denominator is always positive. Numerator, negative 1 minus a. A is at most 1 or negative 1, right? So this, the top part is less than 0. You can observe quickly. So therefore, this discrete time system is stable, but it's not SPR. If you use MATLAB, you can see the frequency response will look like something like this. This is when omega equals pi, and then this is omega equals negative pi, the value of this number. So those are the very practical conditions to evaluate whether LTI block is SPR. Okay? So, as a recap, it is a fact that LTI systems, SPR is strict passivity. So that's how it connects to our prior general concept. Okay? So the full statement is if it's positive real, if it's not strict, then it is passive. It's sometimes interesting. Although positive real is less restrictive than strictly positive real, but to process that actually is a little bit more involved. That's similar to the concept of marginal stability and stability. Strict stability is actually very easy. You just require the poles to be either strictly on the left half plane or within the unit circle. But when you have marginal poles, let's say you have 2 poles at the origin, you have a double integrator. You have 2 marginally stable poles, the system is unstable. So these are the interesting practical aspects about these concepts. Let's talk about PR. And then when we talk about PR, I hope you will be able to gain a little bit more understanding about the naming, the convention, about positive real. All right? It is, maybe you're still confused why under this condition it is called strictly positive real. Okay? Now let's talk about the PR condition. PR condition for continuous time is as follows. So transfer function GS is single input, single output. All of the discussions here are single input, single output transfer functions. is PR if it satisfies two conditions. First condition is if you treat this as a function and then the input s is a real number, then the output is going to be a real number. This is usually not difficult. If you think about transfer function, you replace s with some real numbers, then the transfer function is going to be real. The second condition is if you evaluate this complex function, if s is on the right half plane, strictly on the right half plane, then the real part of this complex number will be guaranteed to be on the right half plane strictly. This is a little bit more than this condition, but it explains the name better. The name is saying positive real. Okay, you can see this is really saying this is the positive side, this is the real side. It's saying the function, it is real if s is real. It is saying the function, it is positive, the real part of this complex number is positive if the real part of s is positive. So that's better explains the name, but for now it may be extremely non-intuitive how I'm going to evaluate this, right? It's going to be very difficult if you think about how to do this very quickly. Okay, you can't just choose all s on the right half plane and evaluate this condition to check the PR positive realness, right? This is extremely not so practical. So turns out this is equivalent to some conditions that are looking like this. It is equivalent to three conditions. First of all, it is stable. Right? It doesn't have any poles in the right half plane. It can have poles on the imaginary axis. So it can be marginally stable. But if it has any poles that are marginally stable, then they are simple poles. They don't repeat. Right? So this is a double integrator can't be positive real. It cannot have repeated marginally stable poles. That is somewhat expected, right? If you have repeated poles that are on the imaginary axis, then it's going to be unstable, the transfer function. So it doesn't have these troublesome poles, and then the residual residual is positive, not negative. All right? So basically, this is saying repeated troublesome poles cannot exist. If you do partial fraction expansion, so the concept of residuals appear in the partial fraction expansion of a transfer function. It is saying the residual, if you do partial fraction expansion for these marginally stable poles, is going to have a positive, non-negative residual. And thirdly, something similar to this. It is the same concept of a frequency response. If you evaluate the frequency response of the transfer function, it is non-negative. Okay? Here is strictly positive. This is positive. It can be 0. Okay? Those are the conditions, practical evaluation of a positive real transfer function, these conditions. Okay? So these two equivalents, I won't talk too much details about it here. These are from calculus. And some general concepts they're very powerful calculus results for these. Names such as Cauchy integral theorem, maximum modulus theory. It actually says something, I will give some intuition about it. All right? In many cases, for complex functions, it turns out we don't have to evaluate everything in this complex domain. Many times, the extreme values will occur on the boundaries. Okay? That's what is happening here. This is on the entire complex right half plane, but it turns out, after some calculus, if we look at the boundary of this domain, we will be able to explain its nice properties, such as being positive, non-negative. That's the basic concept. All I'm saying is, it's great. We should appreciate the fact that we can evaluate this seemingly non-intuitive definition by just looking at the frequency response on the imaginary axis. I'll introduce the discrete time definition. So the discrete time positive real definition is a single input, single output transfer function if this time I will just use the equivalent definitions here. No poles that are unstable. And then if it has marginally stable pole, it won't repeat. And the associated residual is non-negative. And then the frequency response the real part of the frequency response is non-negative. very similar to the continuous time definition here. The difference is just how you evaluate the frequency response. All right, so that's about the content for today.